Hello everyone. Today we will be solving question number 4 from IOAA 2025 theory part. So it's based on extinction and stellar physics. So it's called Balmer decrement. Consider a main sequence star surrounded by a nebula, and the observed V band magnitude of a star is 11.315 Mach. So the V band magnitude, the observed one is 11.315 Mach. The ionized region of a nebula close to the star emit H alpha and H beta line, which wavelength has been provided. So we have been provided a wavelength of H alpha, which is 0.6563 micrometer, as well as H beta, which is 0.4861. Now the theoretically predicted ratio of the flux in H alpha to H beta lineage. So we also have been provided a flux ratio. Okay, which is 2.86. However, when this radiation passes through the outer portion of the cool dusty nebula, the observed emission fluxes. So we have been also provided observed emission fluxes. This H alpha observed is 6.80 into 10 to the power minus 15 watt per meter square, as well as for beta, at beta line it's 1.06 into 10 to the power minus 15 watt per meter square, right? The extinction A lambda is a function of wavelength and is expressed as so we have also been provided the function of A extinction, where K lambda is the extinction curve and then EV minus B denotes the color axis, right? And similar to that, we also have been provided the function or relation for K lambda. So if my lambda is 0.63 to 2.20, I need to use this relation, and then 0.12 to 0. Less than 0.63, I need to use this relation. Whereas RV is given by my extension divided by color axis, which is equal to 3.1, and it is called total to selective extinction, right? So what does this question represent? Okay, let's picturize this question. uh, there's a star, right? There's a star, and then there's a nebula. It is surrounding. So nebula is just a cloud of gas and dust, right? And then we have been told that uh, the region which is close to the star ionization, because of their ionized H alpha and H beta is emitted, right? And then my this light passes through the nebula, and because of the light passes through the nebula, I observed some light which has been observed as H alpha 0 and H beta 0 observed, right? And why is it happening? Why am I obtaining a different value for when passing through some gas or dust? Is it because of a why so? It's just because of a extinction. So I can simply say extinction, because of extinction. So what does extinction exactly mean? So extinction simply means that it is like dimming or reddening of a light. So light from star celestial object when light passes through gas or duster, and they absorb they absorb or scatter the light. So because of that, because of the extinction, we observed a different light. So I can write my extinction as I can also write extinction as extinction is denoted by A as m observed minus m intrinsic. So this is a magnitude, observed magnitude, which we observed magnitude, and this is intrinsic, or I can simply write emitted, which is if the space between, if space between my star is empty, then the magnitude that I observe, the magnitude observed is this, intrinsic. So it's emitted magnitude when there is no any ISM or any material is presented, right? So it can be like, if there is no ISM or dust present, I will observe my M intrinsic, and if there is any ISM or any dust, and then the light passes through it, or they get scattered or absorbed, and because of that I observe something that is called M observed, and the factor that is occurring, that is called extinction. Okay, so I guess extinction is clear. And so now my question says that I need to find the value of a kh alpha and kh beta. We have been provided a relation for that. We have been provided a relation for a k lambda, which is a function of lambda. And then for 0.63 to 2.20, this is the relation that I need to use. And I know for h alpha, it's 0.653 line in this value. So I can simply write, for that I can simply write k h alpha can be simply written by writing that relation. It's 2.659 multiplied minus 1.857 plus 1.040 divided by 0.6563 plus 3.1, which is 2.4. Similarly, if I go into this relation, my lambda value for h beta lies in this range, so I can use this relation, which will be k h beta 2.659 minus 2.56 plus 1.509 divided by 0.4861 and so on, right? It's plus 3.1 and plus 3.1, and it turns out to be 3.6. Okay, so part A of the problem has been done. Now my part B says that find the value of a ratio for a color axis. So the ratio has to be determined. My ratio is, so I need to find E h beta minus h alpha E b minus a. So before solving this question, let us know what color axis means. So what does color axis means? Color axis means what? And before understanding color axis, we need to understand color index. We need to understand the color index, right? So color index. So if I want to define a color index tells me the color of a star. Simply, how it is defined? It is defined as difference in magnitude of two different filter when observed in two different filter. When observed in two different filter. So if I say B minus V, This is a color index. I am saying that I want to subtract magnitude when I observed in V filter minus magnitude I observed when I observed star in V filter. If I subtract this, then I obtain a color index. And then color index is used to measure the temp. It is used to for the relation of a temperature, how hot my star is. This is used for um, to observe how it lies in blue spectrum or a red spectrum. So similarly now color axis. So if my color index is 0, and then now color axis, it is denoted by EB minus V, and then it is defined as B minus V observed minus B minus V intrinsic. So what does this mean? It means that my how much color observed is changed due to extinction. This is provided by color axis, and this is provided by color axis. So uh, if I'm observing a star, and then I find that okay, if there is no ISM present, if no ISM, like space is empty, I get a color index of V minus V, which is intrinsic, right? And then now, if uh, ISM, dust, gas is present, I will observe a color index V minus V, which is observed, and uh, this difference is given by color axis. So now I hope you get what color axis means. So in my question, it is asking me E H beta minus H alpha divided by E H B minus B. So it is simply saying that I need to find the color axis for H beta and H alpha, and then I need to get this difference. The color index in H beta and H alpha, and then I need to also find the color index in this one B minus V filter, uh, and then I need to find their value. This is what the question means. So how to find that? We have been provided a relation uh, for a lambda, which is extinction. We have been given a extinction as a function of lambda, and then it has some value, right? So let us suppose we are observing let us suppose we are observing x band, and then in y band as well. These are some hypothetical band that we are observing. Now I can simply write my x band observed. If I observe x band, it should be equal to x intrinsic plus a for that x, which is extinction for that band, right? So for y band, it is y observing x sorry y intrinsic plus ay, extinction for that band. So now this is extinction in x band, and then this is in y band, and I'm observing and I'm getting a magnitude. I'm observing and I'm getting magnitude as such with this, right? Now I can write this. If I get into this, x minus y observation minus x minus y intrinsic gives me ax minus ay, right? So what does this mean? there is an important relation that we get from that. The color axis for two different wavelengths, alien wavelength, is just the difference in their extinction. So E H beta minus H alpha would be what? It is just the extinction in H beta line minus extinction in H alpha line. Right? Now I already know the relation for lambda. A lambda is B minus V, E B minus V. I know this relation. So for A H beta, it should be K H beta E B minus V, and then for A H alpha, extinction H alpha, it should be K H alpha E B minus V. So if I can now, I can write this relation as E H beta H alpha as KH KH beta, sorry, KH beta minus KH alpha EB minus V, right? So this equation becomes EH beta minus H alpha divided by EB minus V, and I know the relation of KH beta and KH alpha. We got this value right from here. So we got this value as 3.6 and 2.4. So it's 3.6 minus 2.4, and this is 1.2. This is the value of second question. Now let us look into the third part of the question. It says that estimate the extinction due to nebula AH alpha, so AH alpha and AH beta, at H alpha and H beta wavelength, respectively. So now my question is asking me to find extinction due to nebula of at H alpha and H beta wavelength. These are AH alpha and AH beta, right? And then for part 3, we are supposed to find AH alpha, AH beta. What are these values? So we already saw from the figure we draw above, because of a nebula the extinction occur, and I get some observed value, right? And then there's one relation that we defined, as suppose this is the relation that we defined what extinction means. So from we defined as A M observed minus M intrinsic, right? Now we know the magnitude relation. For a magnitude formula, m1 minus m2 is equal to minus 2.5 log of flux for that object, f1 first object, and flux of 2. So I find if I use this relation, I can extinction can be written as minus 2.5 log of flux observed, flux intrinsic, right? You can write this for uh, any lambda, for any wavelength. A lambda equals to minus 2.5 log of f observed at that wavelength and f intrinsic at that wavelength. We got this value, right? Okay. Now, so for AH beta, I can write at 2.5 log of f observed at H beta wavelength, f intrinsic, this wavelength. Oh, sorry, it's H beta. right? And similarly for alpha minus 2.5 log of f observed at that wavelength, and then f intrinsic at that wavelength. These two are the relation. Now, how do you find the flux for observed flux and f intrinsic flux, and then f observed flux for h alpha and h beta both? How do you define that? Okay, so if you look into the question, we saw this value. This is a flux for h alpha and h beta. So this is the ratio of a flux. That is, this is intrinsic. If there is no any ISM present, the H alpha and H beta, their wavelength is this, and their theoretical predicted ratio is given by this 2.86, which have been provided. So that means a theoretical predicted ratio for a flux is given by 2.86, which is for an intrinsic. That is, if no ISM or no any dust or gas is present, then the ratio for a flux is given by this 2.86. But also we are told that the flux that we observed, the flux that we observed has been provided this, uh, right? So it is saying that if there were no any, so it just means that if there is no any ISM present, and H alpha and H beta flux would have been f alpha and f beta has been this. But since after their flux we have been provided there, now we are observing flux of H alpha observed and f alpha beta observed. This is case that has been provided by the question. So now we have been told that we have been given f H alpha intrinsic and f H beta intrinsic is 2.86. This is equation 1. We have been provided that. Now, how do you define this? We already saw from part 2 of the question. If I subtract this extinction for AH beta and AH alpha, if I subtract these two equations, I get, if I subtract extinction of uh, AH beta and AH alpha, we already saw from this relation, we get color axis in H beta and H alpha, right? We get this. We already saw this relation. So if I just write this as minus 2.5 log of fh beta observed, fh beta intrinsic minus 2. It's minus minus plus 2.5 log of fh alpha observed, fh alpha intrinsic. Now I will take minus 2.5 common, log of fh beta observed, fh beta intrinsic. It's minus log of fh alpha observed, fh alpha intrinsic, right? So now from log relation, log a minus log b can be written as log a by b. So my above equation can be written as minus 2.5 log of, it's fh beta observed, my fh alpha observed multiply fh alpha intrinsic, fh beta intrinsic, which is equal to this. Now this whole this whole is 2.86, 2.86, and similarly we can find the relation from that observed one. This is, if I just use this one, I can find the relation for that, right? So if I can just write the relation now, this would be minus 2.5, sorry, minus 2.5 log of 1.06 into 10 to the power minus 15 divided by 6.8 into 10 to the power minus 15 multiplied by 2.86. These are the observed flux for H beta and S alpha line that has been provided, and this is theoretical. And this is 0.88. So we get E H beta minus H alpha is 0.88. Right? Now EH beta is equals to 1.2 EB minus V equals to 0.88, implies that EB minus V is 0.88 divided by 1.2 is 0.73. Now we got EH. Now we got two different equations. This has been provided and this has been provided. So my question says that we need to find the extinction. This value I need to find. What are this value? Sorry, yeah, I need to find what is this value. But we found EH beta and then EB minus V. Why are you finding EB minus V? If you look into the equation, if you look into this equation, we already found K lambda. And if you find EV minus V, I can find extinction for any of the wavelength, right? So if I already found in part 1 K lambda, and then if I find EV minus B, I can simply find A lambda. And so just to find EV minus V, use this relation which has been provided, right? We have been provided this relation, and from this relation we found H beta minus H alpha, color in excess color for H beta and H alpha line. And then from this relation between EH beta and EB minus B, which has been already defined in our second part of the equation, we found EB minus B. Now we know EB minus B, K lambda. This is same for both, and this we already know for K H alpha and then K H beta. Both has been found. Now I can simply use the extinction formula that has provided in my part 1. This is my this formula. Extinction is a function of wavelength. Now I can simply write this as A for H beta. Can we simply write K H beta E B minus V, which is K H beta is K H beta 3.6. Yeah, 3.6. 3.6 multiply, and this relation is 0.73, and this turns out to be 2.69. And then similarly for AH alpha, I can write KH alpha EB minus V, which is 2.4 into 0.73 as 1.8 max, right? This is a part 3 of our question. Uh, Now part 4 says estimate the extinction of a nebula AV and the apparent magnitude of a star in V man. Okay, so now we found the extinction is H alpha and H beta. Now we need to find the extinction in V band, that is visual band, uh, and then magnitude MV naught, which is absence of nebula, that is apparent magnitude of nebula. So my question is saying, find AV extinction in V band and M intrinsic for V band. So V band M intrinsic I need to find. That is my question. Okay. So now if I go into the question, I saw the relation. Which is my extinction in visual band divided by color axis gives me 3.1. And since I already found EV minus B, I can write AV as 3.1 multiply EV minus B, and now we already found EV minus B, which is 0.73 as 3.1 into 0.73, which turns out to be 2.3. Right now we already know A extinction is M observed minus M intrinsic, and we have been provided that observed magnitude, we have been said that the observed V band magnitude is 11.315, and the observed V band magnitude is 11.315. So its AV can be written as 11.315 minus M intrinsic, and then I already know M intrinsic as 11.315 minus 2.3, which is 9, yeah, approximately 9. So it's approximately 9 mag. This is again. So this is how we solve the problem. This problem is easy but conceptually heavy. I hope you like the solution of the problem. Thank you.